Hello, everybody. I'm Ishan, and I'm going to be introducing our presentation for Checkpoint 3. So, to start off, I would like to talk about the model linearity. Can we go to the next slide? Yeah. So, here we first analyze the residuals versus the fitted values. Here on the x-axis, you can see the fitted values plotted against the residuals. Here, from my analysis, I saw that there's a slight curvature that shows up as we increase the fitted values, where around the 2000 mark, we see the point starting to diverge from the 0 point on the residual. This shows that we are missing some sort of pattern within the model, and there's some sort of inherent bias within the model that's not able to capture this heteroscedasticity. So, moving on, I would also like to introduce the test about these individual independent variables within the model itself. First, we took the partial residual plots with the not graduating high school variable. Here, I see a linear trend, which is positively related with the violent crimes, which basically means that the linearity in this case is satisfied, even though it diverges a little bit in the middle, but it overall just maintains a linear pattern. Moving on to the next variable, we see the percentage that are not employed. Here, this also has a strong association with violent crime rates, and it mostly grows linearly as the percentage unemployed increases. And moving on, we also looked at median income. Here, there was a negative relationship, which basically means as median income increased, we saw a reduction in the crime rate, which basically makes sense because as we increase income, crime rate is supposed to be reducing. Finally, we also looked at the urbanization. Here, we saw some interesting results, mainly because the data points within the data set did not have, they had a skewed amount of data where we had a lot of urbanization and we had less amount of urbanization. So as we look at these two trends, we also see that there is a very less relation to how the violent crime rate is being assumed. So we don't really see that big of a linear association between these two variables. Finally, I would also like to talk about how the constant variance in this data set is assumed. Here we see the scale location plot, but here also we see a increasing spread, which basically says that the constant variance assumption within the model is inherently broken. So some other solutions are either we transform one of the variables, either the y variable or x variable, and we also need to look at how or which variable we need to change. If we move on, the Bruce-Pagan test that we analyzed. Here we can see that there's a BP rating of 185.75, which basically says that there is the constant variance assumption is basically broken and we have to reject that. So we have to create a model in such a way that we either transform the variable or we perform some other statistical methods to fix this issue within the model.
And then we'll test the normality of this data set of this model. And by showing the histogram of the residuals, we found that the patterns, it shows that it is extremely left skewed. And so not, it showed that it is not in a bell shape. So it indicates that it is not a normal distribution. And also we applied the QQ plot. Uh, According to the graph, as you can see that the points are mostly focused on the straight line, but when the values get larger and or it goes to its left tail in the negative side, and it will shows patterns of deviation, um, which shows that it has the probability that it is not a normal distribution for this model. And also last we applied the Shapiro-Wilk test. For this test, the original hypothesis is that residuals are normally distributed, and the alternative hypothesis is that residuals are not normally distributed. And by applying this normality test, we found that the p-value is extremely small, which is much less than 0.005. So we are statistically confident to reject the original hypothesis so that we can conclude that residuals are not normally distributed. So, our next step is to find our outliers in this model. And we use the Cook's distance. And Cook's distance measures how much the entire regression model would change if our particular observation were removed. And we apply this model showing that there are uh, several observations are quite deviate from the mean value, but the distance range is within the 0.05, which shows that they are not so influential as an outlier. So we will apply our next test, the leverage test. The leverage value measures how far a data point's the predicted values are from the mean of all predictor values. And the red line shows the mean values of this model. And so that there are several observations is far away from this value. So we can pay more attention to these values that are far away from these. But the leverage value of these observations are still within 0.03, which shows that they are still not so influential as an outlier. As conclusions, the first graph shows the residual values versus the fitted value. And according to the graph, the relationship between predictors and the dependent variable may not be perfectly linear because they are not distributed randomly in the graph. And the second graph is the QQ plot. The residuals are not perfectly normal, possibly affected by the extreme observations, as I mentioned before. And also the third graph is about the scale location plot. It shows the evidence of heteroscedastic, not constant variance, and suggesting that the model errors are larger for higher predicted values. And the last graph shows the residual values versus the leverage values, which shows that some observations are influential observations as an outlier.
So for the last part of checkpoint three, we um, see the interaction effect of unemployment and unemployment, which is a continuous variable, with the poverty tiers, um, and the effect of both of these on violent crime rates violent crime rates. So first we look at the summary of the model. We can see that the estimate, which shows us the direction and magnitude of the effect, is about 421.5, um, which means that violent crime rates are 421 points higher compared to lower poverty areas, holding other factors constant. Then we can look at the p-values using the rule of thumb that the p-value should be less than 0.05 to indicate any significant effect. Um, we can see that high poverty tiers have significant p-values, which is less than 0.001, which suggests strong evidence that how high poverty is linked to higher crime. All other predictors and interaction terms have p-values above 0.05, so they were not statistically significant. Then we look at the F statistic, which is about 161.3. Um, and this tells us that our overall model is statistically significant, which means that at least one of our predictors explains uh, real differences in crime rates across communities. Then we look at the R squared, which is around 0.3, which means that 30% of the variation in violent crime rates um, is explained by unemployment and poverty rates as predictors. That's a moderate level, but it is meaningful for social data like this. Then on the right, we can look at the graph, which shows how the unemployment rate and poverty tier relate to violent crimes. Violent crime increases slightly with unemployment across all tiers, but slopes are similar, meaning unemployment affects crime similarly everywhere. The blue line, which is the high poverty areas, start much higher, showing that these areas consistently have high crime rates overall. Thank you.